the afternoon session. The first speaker is Voigt, who will tell us about the string group and vertex algebras.
Thanks very much. Thank the organizers for the invitation. It's really very nice to be here, and I'm glad that I have the opportunity to speak. So, right, what I want to talk about is related to the string group. So let me start by telling you a little bit about the string group. Okay, so here it is. So if you like, it's defined to be the three connected cover of the orthogonal group ON. So you pick, so and yeah. So if you want, you can start by looking at it like this. So fix the Euclidean vector space Rn, then the orthogonal group On acts on that. And well, this is a nice Lie group, but it's not connected. So if you want a connected group instead of On, well, then you just pass to the connected component. So passing from On to SON, that means in topologist terms killing pi naught, so moving to the connected component. Well, then SON, well, it's again a nice Lie group, but as you know, it's not simply connected. So if you want to improve on that, well, again, fairly standard procedure, you pass to the universal covering, which is spin n. So in this way, again, in topologist terms, you kill pi 1, the next non-trivial homotopy group. And then you can ask, okay, so what happens if I continue in that way, if I kill more and more of the low-dimensional homotopy groups? Well, actually, pi 2 is already 0 for spin n, so there is nothing, in a sense, in the next step, but pi 3 is non-zero. So you could go and kill pi 3, make that 0, and then what you get is what people call string n. Okay. Now, this doesn't tell you terribly much about what it really is, and I will say a bit more about it in a few minutes. But so maybe important remark, it's not a Lie group like the other three guys here. So it's a more complicated object, and actually in the past 10 or 15 years there has been a lot of work by various people to give nice models for string n, emphasizing various features of it. So I'll not try to attempt to review the history here. As I said, I will focus on one particular model a bit later. But what came out of this study is that actually, in order to understand string n, it's best to not view it as a group, but in fact as a two group or as a categorified group. And okay, I'll also explain in more detail what that means a little bit later. Now you may ask, okay, so why would I bother to look at that at all? I mean, so the reason that well, one would like to understand more about string n is that the philosophy is that in the context of supersymmetric sigma models, string n plays the same role as the spin group spin n plays for, say, supersymmetric quantum mechanics or spin geometry. And well, ideally one would like to transport some of the things one can do in spin geometry to this infinite dimensional setting. And well, one thing you could in particular try to look at is whether you can make sense of something like a Clifford algebra analog for string n as well the usual Clifford algebras, which are very useful to study spin groups. And that's basically what I will talk about. I should say straight away, this is a work in progress and has been so already in a while, and so I'll explain you some of the ingredients, but it's not a finished project, and there are still yeah, things that one has to work out and prove in particular. So yeah, in that sense, this is all with a grain of salt maybe. But right, let me tell you the plan of my talk. So I'll first try to explain you a bit more about string n. So I'll give you a more explicit description of what it is or how to think about it, and then following up on what I just said. So ideally, one would like to develop some theory which is similar to what one can do in finite dimensions for the spin group, in particular construct Clifford algebras and spinors. So I'll review the finite dimensional setting, which is basically going to be all well-known and easy stuff, but I will present it in such a way in which, well, it's at least from what I want to talk about later, suggestive to what one should expect in the infinite dimensional setting. And then, okay, as an ingredient in that, we will look at vertex algebras. So I'll say a bit about that, and then I'll tell you, well, what this categorical Clifford algebra should be. Okay, right. So before getting into all of that, so I mean I have used that word, I guess, a few times already, categorical or categorifying. So maybe just let me say a few words about that. So what is categorification? So what does that all what does that mean? Well, if you look it up on Wikipedia, that's what you will find. And yeah, so I don't know whether this makes sense, but let me give you maybe some examples of what would fall under this badge of categorification. So it's not really a precise procedure, it's just maybe a terminology for describing various things you can do. And one example, I guess, which everybody here knows would be tensor categories. And well, if you have, say, I don't know, whatever flavor of tensor category you want, maybe a fusion category, then you could look at the fusion ring, right? That would be, in a sense, a ring you can associate to that. But the category, of course, has more information, and well, in a sense, it is a categorification of the fusion ring. So that's one way to think about it. I mean, it doesn't really help you much if you want to study fusion categories, but at least that's maybe one way to look at it. Well, the second example again is also just maybe a curiosity. Well, Fock space, you can do that as a categorification of the exponential map. Well, this will not prove you any theorems, but well, it can be at least a nice way to think about that. And then the final point on my list, that's what I want to expand on a bit more in the sequel, and that's also basically a setting where you really gain something, in a sense, from looking at this categorical picture. So if you want to study, I mean, symmetries of spaces, say, then, well, you would look at group theory. And, well, if you want to look at symmetries of categories, you should look at the corresponding analog of groups in the categorical world, and that's basically what these categorical groups are. Okay. So let's take a look at that. So categorifying the concept of a group. Here it is. So well, as I said, so basically a group is a set with some further structure. You have this group law from G cross G to G, satisfying some axioms, associativity, existence of unit, and so on. Well, now, if you want to go one categorical layer up, you would start from a category, which I write boldface G for categories here. And, well, the group law should now be, well, a functor from G cross G to G, and you, well, would expect to have to add some further structure to that. And yeah, now the thing is, once you are in this categorical world, there are different flavors in how strict you can require your structure to be. And so what I've written down here is what one often calls a strict two-group. So that would be a category with functors, so a multiplication functor if you like, an inverse functor, and the identity, the unit functor, which satisfy the group axioms really on the nose. So if you apply M cross identity M, so the associativity should really hold strictly on the nose, like in a strict monoidal category. Okay, but you can do also non-strict things, and I'll also say a little bit about that later. Okay, so well, that's as easy as it is, but let's see how to think about it. So you can think about these strict two groups in different ways. Basically, the way I have defined it here, that would be, well, group objects in small categories. Well, that might not be much more appealing than what I put on the previous slide. And there are some other ways to state it. The last term on my list is perhaps the most, I don't know, accessible one, the most easy to describe one, namely cross modules of groups. I mean, this also has a long history. Here's the definition. So basically, cross module of groups consists of two groups, E and N, together with certain homomorphisms, D and alpha, such that these two conditions are satisfied. So the first condition basically says that the conjugation map is, say the D is equivariant with respect to conjugation, if you like, and then there is the second identity. And okay, maybe you look at this, if you haven't seen it before, you might say, well, so why that? Basically, the idea is that cross modules can be thought of as three-step extensions of groups. So you would have a sequence like this. So N and E are the two constituents in my cross module. That's the thing I start from. And then I have this map D, and I can take the kernel and the quotient. So it turns out from the axioms that actually N is a normal, so the image of N in E is a normal subgroup. I can take the quotient. And the kernel of delta, well, that turns out to be an abelian group by looking at these two axioms. And well, that might be well, a more, I don't know, hands-on way to think about these two groups. And the thing is, starting from a cross module, if you like, a three-step extension, a little bit extra data, it's also not hard to write down what this strict two-group corresponding to it actually is. So the underlying groupoid is just the action groupoid of N on the space E, so disregarding the fact that E is also a group. And then, yeah, basically the multiplication is the additional structure that comes from multiplication in E on the level of objects. Okay, so at least, I mean, the point here so far is just, so if you like, these categorical groups in the strict sense are essentially three-step extensions, but you can also, in a very explicit way, pass back to this categorical way of thinking about them in terms of groupoids. Okay, right, so let's take a look at the string group again. So here, this is a model developed by Bayes, Krantz, Stevens, and Schreiber a while back. So yeah, so let's have a look at that. So I've written down basically the cross module corresponding to it, and yeah, so here you can see the ingredients. So we look at essentially the loop group of spin n and the path group, and okay, omega hat is the universal central extension pulled back to based loops, And well, then you have evaluation. So from paths into spin, you can evaluate at the endpoint. And the kernel of this map from omega hat spin n to p spin n is a U1. Okay, and now the theorem part of this is that this realizes the string group. So if you take geometric realization of that, you get the right homotopy type, basically. So that's, yeah, but perhaps it's best to think about this string group in this way as a two group. Okay, right, and okay, so here you see already some ingredients which, I don't know, also pop up in conformal field theory, and so that might be a hint already that there is a connection. But before going any further, let me try to give you a geometric picture of, well, maybe how to think about string, the string group. The only caveat is that the geometry will be very, very basic, and also the picture is not really for the string group, but for something simpler than that. So, but anyway, let me try to explain that, this geometric way, perhaps, of thinking about what the structure that appeared on the previous slide might be related to. Okay, so let's fix our group G to be spin n, and let's consider the trivial G principal bundle over S1. I mean, there is just the trivial bundle. So in this sense, there is not that much interesting geometry here. And let's also fix a trivialization of that bundle. So if you like, just the one I've written down there. And now I want to associate to that a category X, where the objects of X are all G connections on that trivial bundle. And the morphisms are supposed to be, so there are supposed to be no morphisms if two connections have different holonomy. Now at that point you might object, hang on a second, so this might depend on where I pick my base point to compute the holonomy. But since my bundle is trivial, actually one can make sense of that independently of where I start computing the holonomy. So that makes sense actually in this setting. And now if omega and omega prime have the same holonomy, I declare a morphism between the two to be a bundle isomorphism which maps horizontal subspaces to horizontal subspaces. Okay, so that's a very natural thing to look at. And now I claim that this is basically acted upon by the two group corresponding to this guy down here, which looks almost like a string two group, except that I have, in a sense, made things simpler over here. And how does that work? Well, if you fix a base point in the circle, then, well, how can you describe your connection? You can just compute the holonomy starting from that base point, and you get a path. And by the way this is all done, essentially, well, that can be viewed as an object in this two group, and also the morphisms. I mean, it's all made in such a way that basically once you fix such a base point, you really essentially get just a copy of this corresponding two group. Now, as I said, so this is not the string two group. And in a sense, actually, this is the two group version of the spin group. Okay, so much simpler. But the reason I wanted to explain this is that, in a sense, this is, or this should be the analog of going from, or so if we go back to this analogy with the finite dimension situation, there you would go from SON to spin n, and in a sense now we want to go from spin n to string n, and here is in a sense what corresponds to SON in the spin geometry situation. So there we would start with the Euclidean vector space, and you could look at all possible orthonormal frames in that vector space, and in a sense this is supposed to be the analog of that for the string group. Okay, Right. So that much about the string group itself. So let me now tell you a little bit, a quick review about Clifford algebras. So this is now going to be very easy, basic linear algebra. Here it is. So we fix n, and we look at the algebra generated by the Clifford relations, which I've written down there. And as you know, I mean, this can be easily computed and identified. So here's what you get. In even dimensions, you get just a full matrix algebra, and in odd dimension, you get a copy of two matrix algebras like that. Okay, and one can also write down explicit isomorphisms. So that's all very nice. Now, okay, as I already indicated, so one of the virtues of Clifford algebras is that they allow you to give a very nice definition of spin groups. And how does that work? Let me have a look at that. So if, well, inside the Clifford algebra, you can identify the real linear span of your bases, your generators. And now that spans a copy of Rn, and you can generate a subgroup of the unitary group of CLN by just taking an even number of products of unit vectors in that subspace. Okay, and moreover, also not hard to check that if you look at the conjugation action of spin n on CLN, that will preserve this subspace Rn, and in this way, well, you will get a map from spin n to SON, and in this way one obtains the universal central extension of SON. Okay. Right. Now, spinors. Let's basically from now on I'll restrict myself to even dimensions. So n will be an even number, and yeah, in this case, I mean, the Clifford algebra is just a full matrix algebra, so it's easy. I mean, it's completely obvious what the irreducible representations are. It's just column vectors of the right size. But for what I want to talk about later on, it's kind of useful to explicitly construct that from the data we started with, so without relying on this isomorphism up there to begin with. And one way to do that is, well, you first complexify your space V, and you pick a polarization in there, by which I just mean complex subspace L, such that if you take the conjugate, so since our space is a complexification, you can take the conjugate subspace, and if you take the sum of these two, that should be an orthogonal direct sum decomposition of the Hilbert space VC. That's one way to phrase that. And once you've got that, you can form the exterior algebra over L, and then you have creation and annihilation operators on that, and you get your spinor module. And okay, so in this way you get this isomorphism CLN with endomorphisms of S, and well, you can also, since it's just a matrix algebra, this is just S tensor S bar, a conjugate Hilbert space if you like, where you just use the matrix multiplication in a sense, yeah, between these two, and well, so that's just one way to look at this. The reason I wrote that down is, I mean, this should be reminiscent a little bit about reminiscent of the splitting in CFT between chiral and anti-chiral parts. That's at least yeah, the way it will reappear later on. Okay. Now, okay, let's even spend a bit more time on that, so really getting down to the bottom of things. If you want to fix a polarization, then one way to do that would be as follows. You view your R to the 2k as C to the k, so as a complex vector space, and then you pick the polarization into plus and minus I eigenvalues of the complex structure J on V. And in this way, basically, I mean, you get all possible polarizations in that way. So it's not really, you're not restricting yourself in any way by doing it that way. So, okay. Now, some additional remarks. Yeah, so if we pick this polarization I indicated on the previous slide, then the unitary group inside the orthogonal group will be the subgroup that stabilizes, well, this Lagrangian L. And if you like, you also have the standard maximal torus inside the unitary group, so these block diagonal sine cosine matrices, and that you can view as yeah, those matrices which basically move around basis vectors that are compatible with the standard flag you can choose in C to the K. So yeah, so as I said, I mean, this might look like totally overkill for understanding what happens in this matrix algebra example, but the reason I'm spending time on this is that actually later on this will reappear. Okay. Now, okay, from what we've done, we can pick an integral version of the Clifford algebra. So if we choose an orthonormal basis of our Lagrangian L, then we can write vectors like this, and you get a basis of the Clifford algebra. And well, also the multiplication in CLN becomes very simple because, I mean, it's just matrix multiplication. And yeah, so this is what it looks like. And in particular, what you can do is you can just pick the Z linear span of these specific vectors, and that will be closed under multiplication. And you can view it as an integral version of the Clifford algebra because, well, if you tensor with the complex numbers, you just get back CLN, right? That's pretty clear. Now, if you, I mean, remember at the start I mentioned this example of tensor categories and the fusion rings, and well, I mean, if you want a categorification in that setting, well, you better start from a ring which has some prescribed basis, right? Then you can hope to well, make it into a category. So typically it would be helpful to have something defined over Z, and that's what we get here. However, of course, this construction depends heavily on the choices we have made, right? So there's nothing canonical about picking these particular choices, and in particular, of course, you will not find an action of ON on this integral version of the Clifford algebra. This is absolutely to be expected because you have fixed all these choices. So yeah, in what I will speak about next, basically the idea will be to first, well, come up with, in a sense, an analog of this integral version of CLN, and then, so that will not be very hard, and then the hard part is to actually yeah, get rid of all the choices that also will be involved in that construction. So in the end, yeah, what should come out of the construction is actually a very big category where yeah, you are no longer making any choices, in the same way as CLN is the thing which doesn't involve any choices. That's the canonical object. Okay, right, so let's see. What's the idea? Well, the starting point is well, not surprising. You start by looking at the Car algebra. So now we replace our finite-dimensional Euclidean space V with a Hilbert space, and we construct the Car algebra. And well, that's very nice C-star algebra. But clearly there's no categorification at this stage. It's just an algebra. So in order to get towards this categorical layer, we have to take a closer look at this, and this is where we're going to run into vertex algebras. So let's see. Right. So I think vertex algebras were already mentioned a couple of times in previous talks, but I'm not sure whether we have actually seen a definition so far. I mean, many of you will know that. Well, anyway, so here is a definition, at least the one that I shall adopt here. So I'll be interested in unitary vertex algebras. So yeah, that has been studied by various people. I think it has been around implicitly for a long time anyway. So, but okay, so one way to phrase that is that, well, you have a state space V, which, so since I'm also interested in super, and the super version of that are allowed to be Z2 graded, and the grading, so will be by half integers, and the integer part, so non-negative half integers, the integer part will be the even part in the Z2 grading, and the half integer part the odd part. And then, yeah, we should also require that we have the vacuum subspace will just be one-dimensional, and all the weight spaces Vn are finite dimensional. So that's my assumption here. Then, yeah, we require an involution, so the analog of a star structure. And Karpi, Kawagashi, Longo, Weiner, they call that the PCT operator. We require the existence of a conformal vector. And then, well, we have a state field correspondence. And we want that to be what I would call locally bounded, by which I mean the energy bounds condition that Karpi and co-authors have used in their paper. So so essentially, I put that here as an ingredient because this will be useful to have in all the examples you can think of. You can check that quite easily. Ideally, I guess you would want to prove it from just the algebraic data, but that seems a bit difficult. Okay, and here are the axioms. So okay, I won't spend much time on that. So if you have seen that before, then this is just basically all the usual stuff. So here, unitarity, that's the additional part which comes in now in this unitary setting, and yeah, one has to be a bit careful to get the formulas and the square root of -1 right here. So one has to decide whether one wants to work with super Hilbert spaces or ordinary Hilbert spaces, and yeah, but yeah, if you interpret this in the right way, then this is basically what you get. Right.
So why you're dropping operator algebras in vertex? So you're dropping
Oh,
for
that's just-
assumption or just for?
I'm just lazy.
Okay.
So yeah, I should say vertex operator algebra all the time. Yeah. Yeah, I know. I mean, maybe this is not good.
Vertex algebra is what Richard Voigt.
I know. So yeah. So basically, from now on, you should always, in your mind, input this word operator everywhere. Okay. So two remarks. I mean, what do we gain by putting in this unitary structure? Well, we can look at, first of all, we can look at the Hilbert space completion of our state space, that's for sure, but we can also do some smaller completions. And in particular, we can look at, well, the Schwarz completion by looking at rapidly decreasing states. And this is useful in various settings because this allows you to do a few constructions which you couldn't do on the purely algebraic level, but for which you also do not necessarily have to pass to the the operator algebra level, or say conformal nets level. So one thing you get from this local boundedness condition or energy bound condition is that you can extend your state field correspondence to something which lives on the Schwarz space. So can map Schwarz states to operator value distributions on S1. So here, yeah, I guess I should explain my notation. So this L or this, okay, I mean, these Schwarz spaces are naturally Fréchet spaces, and yeah, then you can make sense of, well, bounded linear maps between those, and yeah, you get that. So I mean, technically speaking, maybe this is really just a quick side remark. So the best setting to look at that would not be topological vector spaces, but rather phonological ones, because there you have a nice Hom tensor adjunction relation, so you can write things very neatly. But that's really not so important. So the main point is here that you can take your Schwarz states and you can associate to them distributions on S1 with values in bounded endomorphisms of the Schwarz space itself. Okay. Now let's look at two examples. So the ones that I'll be interested in. So we start again from our space V, and we look at polynomial functions with values in the complexification, and I throw in this square root of t parameter, so polynomials in square root of t. That's my basis space, and now I can decompose that into antiperiodic and periodic polynomials. Well, so h and s and h r, and then I can look at polarizations of those. So in the Löwe-Schwarz case, I will look at the following. Well, the usual energy, positive energy polarization, if you like. So I get I get a Lagrangian subspace like this, and I can form the corresponding algebraic Fock space like that. And in a similar way, I can do a construction for this Ramond space, where in addition I should take care of the zero mode part, and yeah, I pick basically spinors for a fixed polarization of this finite dimensional vector space. Anyway, so that's not so important, the second bit. What is important is that you can form a vertex algebra out of this Löwe-Schwarz Fock space, and well, roughly speaking, the construction is like this. You define these generating fields, which I call psi I, which basically, yeah, they look like this, and the psi I, they act by by creation and annihilation operators on your Fock space. And well, once you've got these generating fields, and you have the OPE of those, then there is general machinery which allows you to define the state field correspondence in general, and yeah, so and you get a unitary vertex algebra in that way. Okay, now yeah, let's have a quick look at that as well. Right, if we pick, so L spin is the loop group of spin n, then on this Fock space Fn there is representation of the projective representation of the loop group, and well, there's basically the level 1 representations you can construct in that way, as we have already heard about this morning. And yeah, so you get this behavior for the generating vertex operators basically, and well, that follows immediately from the car relations, and now in claim, so this extends to a bounded linear map actually on the Schwarz spaces in a suitable way. So
L tilde mean here, is it what you call P or something?
no, this L twiddle is the universal central extension. So yeah, so it's a projective representation of the loop group, but it's an honest representation of the central extension. And so here, when I write U gamma, I mean, it doesn't matter which representative you pick, because it, in the conjugation action, this cancels out. Okay, so here I've written claim because yeah, I don't have a. It's one of the things which one should have proved. So formally, this will hold, but the thing here is to really get things yeah, compatible with the if you like, analytical structure. So I mean, I think, yeah, so this should be true. Well, this is one of the, as I said earlier on, this is one of the advantages of passing to this Schwarz completion. You have some more flexibility to do things. Okay. Now, a second example, a little twist of what we've seen already. So in this setting that I'll be interested in, we will have to mimic this choice earlier on when we constructed the polarization of the complexification of V. And remember there we split up our R to the 2k into R into C to the k. And in a similar way, we shall now pair two real fermions to a complex fermion. And yeah, we'll see a bit later, like why that is going to be needed. So basically, the complex fermion vertical algebra on that level is just basically two copies of a real fermion, and well, you can write down the generating fields in this way. Okay, now let me move on a bit. So when you study vertex algebras, you also want to study modules and twisted modules. So here is what you get for a single complex fermion. It doesn't matter so much that it's one-dimensional, but okay. And the situation is very easy. You have one irreducible module, which is just the vertex algebra itself, and you have one what's called canonically twisted module. I'll come back to that a little bit later, which is basically constructed out of this Ramon-Fock space that I mentioned earlier. Okay, and I'm not sure who observed that first. I mean, it's certainly, I mean, if you follow up work of these authors, then you can extract that from there. Okay, now let's take a look at fermion modules, and what I'll do is I'll fix again a flag for C to the k, and I'll fix my standard basis of C to the k. So I mean, apologies that this might all sound very pedantic, that I always mention you want to fix these things, but it turns out that one really has to be very pedantic about that to get things right. Okay, so once we have that, well, we can identify C of k, so k-fold Dirac fermion with just a tensor product of rank 1 complex fermions. And well, and then we can look at in a sense, tensor products of these modules that we have for C1, okay? And I write them like this. So we just plug in one of these Ramond modules in one slot, and then keep the trivial module in all the others. And more generally, we can also pick any multi-index and plug these Ramond modules at the corresponding indices. Okay, that might, I mean, from the notation I'm using here, that might already look very similar to what we saw earlier on, but I mean, so far this is, yeah, I mean, just notation, if you like. Okay, now, well, we can put these all together and we can construct a category. Well, I put CLN sub FB because it depends on these choices, F and B. And well, so we look at all modules over two copies of C of k, which look like the modules that I've written down on the previous slide. So up to isomorphism, the simple modules in this category, they are just of this form. So pick a multi-index and well, look at look at these things. And well, you can then define a product on that in the following way. Basically, you can, now look at intertwiners between these modules, and that's what I mean by this HOM. So that's the space of intertwiners, and then, well, since the structure is very simple, you basically obtain in this way a categorical version or souped up version of a Clifford algebra. So the multiplication is exactly like in finite dimensions. Okay, and now, as I said earlier on, so this is not such a big thing. There's not much going on at this point. The important bit is basically in the finite dimensional case, this would correspond to fixing all the choices that we have made, and we end up with something very rigid, and we wouldn't expect to see much just by looking at these fixed choices. So again, here we have made a lot of choices, and the difficult task is to get rid of all the choices. And essentially, we have to look at more general polarizations than the ones we started from first. Then we have to look at different flags and different bases in each flag. And yeah, so in the sequel, I'll just try to explain, in a sense, a small part of that, namely how to get rid of the choice of the basis. So in a sense, replacing the basis vectors by some equivalent basis vectors. Okay, and for that, we'll have to take a closer look into twisted modules. So we have already seen these Ramond modules in the construction on the previous slide. But yeah, so we'll have to look at more general twistings, basically. And this is in vertex algebra theory. This has been studied. Basically since the very beginnings, and already in the moonshine vertex algebra, this plays a big role. Typically, you would consider twistings with respect to finite order automorphisms, but we need to drop that. We need to allow basically arbitrary automorphisms and say unitary. So, well, what is an automorphism? That's pretty straightforward. Here is two examples. Well, the identity, that might not be so exciting, but in a sense, if you pick the identity in all the constructions that come, then you get ordinary modules as a special case. And this parity automorphism that you always have for free in a vertex superalgebra, this leads to these canonically twisted modules. Okay. Let's see. Yeah, let me briefly explain how these twisted modules are defined. So basically, the main difference to ordinary modules is that we have to allow arbitrary powers of the formal variable x. And okay, so we could also look at exponents in C, but since we're interested in the unitary setting, we will only need real exponents, and then one can define what's called twisted fields for each such exponent, and you get a big space of twisted fields for any Z2 graded vector space. Okay, and you can define locality, and you can define what's called the end product identity. So that's similar to what one does yeah, for ordinary modules, if you like. And well, if you're now given an automorphism, then you can decompose your state space V into spectral subspaces with respect to that automorphism. So that's what it means to have this spectral decomposition. And then one defines a twisted module in the following way. Okay, so again, a list of axioms. The definition, so by the way, that's due to Bakalov, building on, so there was a previous work of Wang, but this is relatively recent, so it's not, I think it was published last year. Okay, so you have essentially the same ingredients as you would have in a definition of an ordinary module, but it looks a bit different and more complicated because yeah, you cannot just say take the Jacobi identity. That would not work in this setting. Okay, now I think I have to keep an eye on the time. So let me roughly explain to you this very first step in trying to make the Clifford algebra independent of choices, and that would be getting rid of bases. And so recall that basically I constructed you a very simple monoidal category, CLV, which depended on a flag and basis. And now, in order to get rid of the choice of bases, we have to enlarge our category. So we have to allow other choices of possible bases, and this basically means that we have to allow certain twisted modules as well. And here, since I'm looking at this very specific way of enlarging things, it's enough to look at paths in the path group of the maximal torus. So, and for that, in turn, it's enough actually to look at just the two-dimensional situation. If you understand how things work there, you can put together things in general. Yeah, so this is very hand-wavy now, but basically what one has to do is one has to go back to this description, this space of connections on the trivial principal bundle, and one has basically, for every choice of trivialization, one has to cook up a vertex algebra, the corresponding twisted modules, and then one has to study how different choices interact with each other. And that's basically where these twistings come from. If you want to compare one choice with another, you will go from modules to twisted modules and vice versa. So that's, roughly speaking, what's happening here. And if you do that, well, then your path group actually acts on this category, and in this way, if you use this notation that I used before, you can think of, so yeah, as I said, so in the complex one-dimensional case, these twistings, the torus would just be EU1, and you can view these holonomies, if you like, as being like complex numbers multiplying those with basis vectors. Okay, so that's what we're doing. We're trying to replace this fixed basis by some other basis, and essentially just another basis which is obtained by multiplying each basis vector with some complex scalar of modulus 1. So very simple thing in a sense, but it already involves quite a bit of work in this categorical setting. Okay, and the interesting thing is, in modulo this claim that I put up earlier, it actually it really does what you would expect. So for instance, multiplying a basis vector here by some scalar would be equivalent to what you could do by multiplying something else with this scalar. So it seems to have the right properties, at least on that level. But as I already said before, in a sense, to really get it all to work, you would have to get rid of the other choices that went into my construction as well, and then also understand like how different choices interact with each other, and that gets actually quite technical and difficult. But yeah, I think I'll stop here. Thanks.
Thank you, Christian. Any questions?
What would be the final goal for this? So you have attached some representations of some object in a category to each of these basis vectors.
Mm-hmm.
Now you want to define objects in some category for every algebra element of this Clifford algebra. What is the categorified algebra in your context?
Yeah, it would be the collection of all these modules, in a sense, you get after getting rid of all the choices. And then the task is basically to extend the multiplication to that big category. So that would be the Clifford algebra, eventually the categorified version of it.
So it's one object for every Clifford algebra element, or something?
Yeah. So in that sense, I mean, yeah, it's a bit a different sort of categorification than perhaps what one would normally think of in terms of what I said at the start with tensor categories and categorifying rings, where you only have finite numbers of objects. But for the reasons that I try to explain, if you do that, I mean, you cannot expect to see the string group as symmetries. That would just be too rigid in a sense. So at least that's what I'm proposing here.
Yes. So is the string group supposed to be the photoequivalences of this category, or can you describe it as the way you describe the spin group sitting inside the?
Ideally,
like the even elements of some.
Yeah, ideally you would really want to copy that description and define the specific object in your category and conjugate and see that you get basically a natural action you get on the Clifford algebra geometrically, if you like. But that's in a sense, that's the big question, whether you can do that. I mean, if not, then I don't know, that might not be so useful, but
Any other questions?
Would it be interesting to categorize? I mean, this is constructed from the free fermion.
mm-hmm.
There's many other super vertex algebras.
Good question. I don't know. So certainly, so I mean, for what I have in mind, I mean, in a sense, why I'm interested in that, the next thing to look at would be free bosons, and there actually can also do some things, but yeah, it gets more complicated. But yeah, I don't know. For other super vertex algebras, I don't know.
Okay, any other questions? Well, let's wrap it up. Thanks again, Christian.